Hello, my name is Zoe Etter, and on behalf of Megan, I'd like to welcome you all to this Megan Masterclass with our guest speaker, Dr. Andrew Quinn. Just before we start, I'd like to ask attendees to please use the Q&A button on your screen to send in your questions at any time during the masterclass. There'll be time for our guests to answer any questions you may have at the end of the session. This webinar will also be available to watch on demand on the Megan website at a later date. So it gives me great pleasure to hand over to Dr. Andrew Quinn, who will officially kick off the webinar. Thank you.
Hi, thank you. And thanks to Megan for putting together this opportunity to present to you all. So today I'm going to be talking about the effect of aging on neuromagnetic power spectra. So when we record data using an MEG scanner or other electrophysiological device, we get time series that look like these. In the background of this plot. So every line here is from a different channel in an MEG recording, and we can see that there's very rapid dynamics over the course of even a few seconds. You can see on the right there's a very prominent alpha oscillation. These kind of oscillations reflect the synchronized activity of large populations of neurons doing computations in the brain. And they change on really fine spatial and temporal timescales. So because they reflect the operation of these neurons, we believe that there's a good reason to believe that clinical effects such as aging and even neurodegeneration might be reflected in these signals. As neurons start to, as the connections between neurons begin to break down and the firing becomes less efficient, populations of neurons might start to behave differently, and the oscillatory signals that we observe within the MEG, we expect to reflect those changes. So if I turn on a pointer. So to summarize this, neurons communicate by sending signals to each other. So these action potentials are little pulses of electricity that go from one neuron to the next. And these have to be sent at a really specific timing to be most effective. And the synchronization of this timing, like two jugglers sending balls to each other, ensures that the information arrives efficiently. The thing is, the signal from one of these neurons is absolutely tiny, and there's no way we would really be able to see it. But fortunately, the brain does us a couple of favors here. So often, very large populations of neurons synchronize their firing together. So rather than one action potential happening at one point in time, there might be many action potentials from many thousands or even millions of neurons happening at a really discrete point in time. Similarly, these action potentials tend to be aligned in space. So particularly in cortex, structures of neurons tend to all point in the same direction. This means that the current flows in the same direction, which means that the magnetic fields propagate out in the same direction. So with these two things combining, it means that these very, very tiny signals actually sum together by alignment in space and time to the point where they can be detected from outside of the skull. And of course, this is what magnetoencephalography is. I know I'm preaching to the choir at this particular audience, but this is really our starting point, that for us, we believe that the MEG signal reflects a very precise and very direct measure of how populations of neurons synchronize and communicate. And we're interested in exploring how that synchronization and communication changes and breaks down across the lifespan. So this is our starting point, the MEG signal. One common way of estimating kind of quantities that we can do statistics on from that MEG signal is called a power spectrum. And this power spectrum you might see in many papers and all over science and engineering. It reflects the absolute or relative contribution to a signal from each of a range of discrete frequency bands. The most common way of estimating this is something called Welch's periodogram. So this is a very classic method from 1967, in which Peter Welch suggested that rather than taking one Fourier transform of an entire dataset, which can be very noisy, that we might mitigate that noise by breaking down the time series into a set of sliding window segments. So here in A, we can see a section of, in this case, EEG data. This can be split up into 2-second sliding windows. So we take each 2-second chunk of data. We then apply what's called a windowing function, basically to smooth out any edge effects on either side of that sliding window segment, and then perform a Fourier transform on each one of those windowed segments. And that gives us this matrix, which is known as the short-time Fourier transform. So here on X, we can see frequency increasing in hertz. So we have very slow frequencies over on the left and very fast frequencies over on the right. In Y, we've got each sliding window segment, and darker colors indicate a larger contribution of this given frequency to that particular segment. What we can see very quickly is that there is some structure here, that around about 9 hertz, we can see in this second half of the time series, quite clear indication that there's a very large magnitude of 9 hertz power during those periods of time. We can also see, however, that there's a lot of noise and a lot of variability. So there's patterns that change between adjacent segments that don't necessarily align up or match each other. What Welch suggested was that we simply take an average over all of our sliding window segments. And by taking that average across all sliding window segments, we will zoom in on the representation of the spectrum that is most consistent across all of our sliding windows. And that gives us the familiar frequency spectrum that we can see here on the right-hand side. So again, we have frequency from slow to fast on X and magnitude on Y, where larger values indicate a greater contribution from that particular frequency. Each line here is a single EEG sensor, and we can see the topography around 9 hertz, suggesting that this large alpha oscillation at 9 hertz peaks around slow frequencies. So it's difficult to overstate the impact of this method. It was developed in 1967, but it's surely one of the foundational methods for frequency analysis across science and engineering. It's the fundamental part of pwelch in MATLAB or scipy.signal.welch in Python. And it's the default spectral density estimate in a large number of signal processing, EEG and MEG software packages. And it's often the benchmark for more advanced analyses. So I tend to do, if I'm doing a complicated analysis like a hidden Markov model, for example, before I do that, I would often compute Welch's periodogram just to take a quick look at the data and make sure that everything's ready for the complicated stuff. However, it's really unchanged since 1967. There's been a couple of tweaks, but the fundamental principles have been really consistent. And that's good, that means it works. But actually what Welch was doing was taking spectrum estimation and treating it as a statistical problem. So how do we get a good estimate of our power spectrum in the presence of noise? And though the Fourier transform hasn't changed since the 60s, our understanding of statistics has. And so what I propose in a recent method is that we can make use of some of these modern statistical methods, such as non-parametric permutations, hierarchical modeling, multiple regression. We could leverage all of these if we rephrase our statistical spectrum estimation as a general linear model rather than a simple average. So in this case, the standard, where Welch's standard approach takes an average across sliding window segments, we would now instead specify a multiple regression or general linear model design matrix. So in this case, we now have our data, which is our short-time Fourier transform. So this is the item to be predicted in the regression. And then our predictors in the design matrix. In this case, we have 6 regressors that we're going to use to describe the change over time at each frequency band in our data. And we can use as predictors anything that we know about the world during which the recording was being made. So in this case, I happen to know that after about 15 seconds into this recording segment, the participants switched from having their eyes open to having their eyes closed. I also know that from some automated artifact labeling that there was a bad segment detected around about 8 to 10 seconds. And we also have recordings of simultaneous eye movements in both the vertical and horizontal plane. So we can take all of this information and fit a regression, which is a linear combination of these values that best describes the information we see in our short-time Fourier transform. So here's an example of a full design matrix. So here on Y, we have all of the observations across an entire data recording. So in this case, we have nearly 1,000 sliding window segments. And we can see the regular switching between the eyes open and eyes closed state of our participant. Our linear trend simply looks for a gradual drift over time. And then we have the occurrence of bad segments and vertical and horizontal eye movements. Once we've fitted the parameters for these, we can then summarize them statistically by using what's called contrast coding. And so here I would specify a contrast for eyes open, and that has the value 1 for the eyes open regressor and 0 for all other regressors. So by including this contrast in my design, it means I don't just get a parameter estimate, but I can also get a t-statistic for this eyes open regressor, telling me the statistical probability that there was that parameter was noticeably different from 0. And of course, we can do this for other regressors as well. So whereas this is an eyes open contrast, if the 1 switches over here, we've suddenly got a vertical eye movement contrast. So if we do this for our eyes open and eyes closed regressors, and we repeat that regression for each point in frequency, the contrast for each of those looks like this. And this looks like our standard power spectrum, and really it is. Because in the case of the GLM design matrix, where we have a constant or categorical regressor, this is broadly equivalent to fitting the mean over segments where that contrast was on. So here we're isolating the mean in the segments when the participant had their eyes open, and here the segments where the participant had their eyes closed. Now we can go even further and combine different regressors in our contrasts. So we could do an equal summation of our eyes open and eyes closed regressors to get the overall mean. Or most interestingly of all, we could do a 1 - 1 contrast to have a look at the difference between the eyes open and eyes closed. And in this case, what we end up with is a statistical estimate of how the spectrum changes over time based on our task structure. So the result of this contrast is called a contrast of parameter estimates. So for that contrast, we get a contrast of parameter estimates, or COPE spectrum, telling us about the effect. We also get a VAR COPE, which is related to the standard error of the effect. So whereas the COPE is the parameter estimate telling us the strength of a relationship, the VAR COPE is telling us the precision with which we think we've estimated that relationship. And then we can scale the COPE by the VAR COPE and get a t-statistic. And this behaves exactly the same as a normal t-statistic in any other context you've encountered it. Except now we have one t-statistic for each frequency in our Fourier transform, giving us a spectrum of t-stats. And in this case, for eyes open minus eyes closed, we get a large number of very negative t-statistics, with the largest effect being around about 9 Hertz. So this is telling us at low frequencies, there was greater spectral magnitude in the eyes closed condition compared to the eyes open. So we think this is a really clean method for exploring quite complicated patterns of spectral change, both within and between participants. And so for the next part of the talk, I'll transition over to talking about healthy aging and the sort of effects that we're going to be trying to quantify using the GLM spectrum. So in the past decade or so, there's been a real explosion in what we know about brain aging, largely driven by the availability of really significantly sized open data sets that many scientists are able to analyze. This has been most prominent in the MRI literature, where data sets are getting now into the many tens of thousands of participants covering the entire lifespan, even before birth. So all the way from fetal through to children, to adults, to older adults, and people with neurodegeneration. And with these, there's been a whole host of work, but what's starting to be well established is the lifespan trajectories of core variables. So things like grey matter volume or hippocampal volume change in a structured way over time, though there is some individual variability. And MRI is starting to give us an idea of how big that variability is in healthy populations, such that we can use that as a comparison to identify people who may be suffering from neurodegeneration or related disorders. EEG and MEG are following close behind, but the datasets haven't quite reached the size of MRI yet. One of the largest ones was in this recent paper, looking at a retrospective hospital EEG cohort of several thousand EEG scans, again covering a really wide range of ages, here from I think down to 2 to 3 months old babies, through adolescence into adulthood and into older adulthood. I think the oldest participant here being around 96 years old. What we can see on the y-axis here is the peak frequency of the alpha oscillation. So that was that 9 Hz posterior rhythm that we identified using this GLM-Spectrum in the first part. What we see is that this starts off very low frequency before it kind of peaks around late adolescence, and then throughout adulthood it's relatively stable and starting to drop off later in life. And this is I think the closest thing we have in electrophysiology as a clearly established trend. This has been replicated and reproduced many, many times. It is, however, relatively simple, and there's some, it's perhaps not the best representation of the amount of richness there is in an EEG or MEG dataset. It can give us a lot more information than this one number. And some recent papers are starting to reflect that with larger MEG datasets becoming available and being able to be analyzed by large numbers of people, we're starting to see that full richness show. So in this example from a recent paper, we can see from a range of different frequency bands what the relationship between the MEG activity was over the course of aging. And we can see that there's a very complicated pattern, that in some regions, in some frequency bands, we have significant decreases. In other regions, in other frequency bands, we have notable increases. So there's a rich pattern of effect that isn't being captured just by these simpler peak frequency metrics. And luckily that there is really an exploding literature looking at these kind of features. So how, what kind of features are changing over age, and what other aspects of aging is that associated with? So is that associated with a change in cognitive performance? Is that associated with a particular neurodegenerative disorder? And a large number of these effects are starting to converge. However, we think we can build on this by using the GLM-Spectrum as a single framework which would allow us to capture those core power spectral effects in one shot. So rather than breaking up our analysis into individual regions and individual frequency bands, the GLM-Spectrum would enable us to look at all frequencies and all regions in one go. Similarly, building on that, because it's a multiple regression, we can build in an assessment of the covariant structure of age and aging-related factors. So there's not one pathway through aging. Age is just a number, and things like grey matter volume, hippocampal volume, and overall health can vary greatly between participants. And by using a multiple regression approach, we can say not just how do things change over age, but how do things change with these other factors, such as structural MRI and health. And finally, we can control for potential confounds. So things like eye movements, head size, head movement, and other things that can influence the MEG signal, we can build in these as confound regressors and to a linear approximation, remove those from our results. So towards this today, I'm going to be looking at the CAMCAN dataset. This is a dataset that's been analyzed by many of the references I showed earlier. One of the remarkable things about this is that there's 600 participants or more, and that they are really beautifully distributed across a very wide age range. Notice we're not going into childhood in this dataset. Everything I'm going to talk about today is across healthy adulthood. So we take the CAMCAN data, we do a whole host of processing on this data to make sure it's ready to analyze. We take the MRI data and process it in FSL, doing a standard structural processing pipeline, mainly to estimate things like gray matter volume, white matter volume, and a few subcortical structures such as the hippocampus. In MEG, we download the data that has been Maxwell filtered by the CAMCAN team and provided on their website. So we download the Maxwell filtered data with MoveComp and TransDef applied from release 5. Then using that as our input, we apply this pre-processing chain where we trim the start of the recording, apply some filters, detect bad segments, detect bad channels, resample the data, use ICA to identify components related to EOG and ECG, interpolate back any bad segments, any bad channels that we've removed earlier on, and then run our first level GLM-Spectrum. So from this point then, we take as our input to this, the input to our GLM-Spectrum, we take as the short time Fourier transform of our pre-processed MEG data. So then we have a number of sliding windows covering our time series, which we truncate to be between 1 and 95 Hertz. We use a 2-second window with a 1-second overlap, and we take the magnitude spectrum rather than the power spectrum. It's a technical point, but the magnitude spectrum is a bit better distributed for regression modeling. So we then model how everything changes over those 2-second windows with the following design matrix. And this will vary for each individual participant. We have one constant regressor fitting the mean, one linear trend looking for drifts over time, one ECG regressor looking at changes in heart rate, a VEOG regressor looking at blinking, and then any bad segments that were detected in the dataset. So we specify the following regression and some very simple contrasts just to identify each regressor in turn. And so for our constant regressor, which is our mean term, it gives us a picture like this for a single participant. And this should look very familiar as a kind of standard power spectrum. So this is very similar to what you'd get from a normal Welch's periodogram, except we've removed additional variability associated with the other regressors. We can see our prominent alpha peak peaking in the posterior cortex, and then a little bit of a beta central peak coming up around 24 Hertz in this participant as well. Critically, we also get a spectrum for each of our covariates. And so we can see where in frequency and in space there has been a linear drift over time, where is changing with heart rate, blinking, and where is most affected by bad segments. And again, this is adaptive to each participant. So frequencies and channels where there is no VEOG effect, the model won't do anything. It will simply fit a value of 0 and the constant will be unaffected. But in channels and frequencies where there's a substantial effect, then this will denoise our estimate of that overall constant. So for each participant then, we take our constant variable, our constant GLM spectrum, which represents the overall power spectrum for each frequency and for each sensor, and we combine those into a further GLM, now at the group level. And here, each observation on Y is now a participant. And here we have 9 regressors covering now between subject predictors. Most importantly, age is the one which is telling us how old that particular participant is. We also include some demographic factors, some acquisition factors such as position in the scanner and head size, and some MRI factors such as gray matter volume and hippocampal volume. And again, we define a set of very simple contrasts, just isolating each regressor in turn. So from this, we get a group level GLM spectrum. So now we've averaged across all of our participants, so this should look a lot smoother than our previous version, which was a single subject. But again, we still see this 9 Hz alpha peak in occipital cortex and our 25 Hz kind of beta band happening in central cortex. We also start to see that a lot more consistent structure in each of those first level predictors. So the group average of the linear trend shows a much clearer effect than our single subject. Now we can clearly see that alpha power seems to be decreasing over the course of the recording. But let's zoom in on the effect of age. So here we have the parameter estimate spectrum of age. So each line is a channel, and each I've drawn a topography showing us the spatial distribution of each coefficient at key frequencies. So our age effect then comes out in this parameter estimate. So a large positive parameter estimate means that that frequency and that channel had a increased in magnitude as participants aged. A large negative effect means that that point decreased in magnitude as participants aged. So we can see a range of different effects. We can see an increase below alpha, a decrease above alpha. And we can see that that pattern is also consistent within source space, though this is also work in progress. We can see this kind of decrease in low frequencies, increase in low alpha, decrease in high alpha, and increase in beta coming out very clearly. What's critical is that this is also super reproducible across datasets. So across 3 different datasets and across 2 different sensor types, we see a very similar pattern. So the MEG UK, Oxford and Cambridge data was collected on the same type of scanner as CamCam. But the MEG UK Nottingham dataset was acquired on a scanner from a different manufacturer. But we still see that overall pattern of effects is extremely consistent and extremely reproducible. So we can supplement this picture, which is just the parameter estimates, with the t-value spectrum and do cluster permutation stats to tell us where the most significant effects are within our dataset. And this finds 4 clusters in the places we would expect. So a low frequency kind of frontal area, a pre-central beta area, and then this kind of intriguing double alpha with a low frequency increase and a high frequency decrease. And again, this pattern of statistics is also very reproducible across our datasets. Now, this double alpha peak doesn't mean that there's 2 things happening. So because we're looking at each individual frequency separately, those 2 alpha peaks are actually telling us about the change in alpha peak frequency across aging. So in young adults in our dataset, they have a median peak frequency of around 10 Hz. But the older adults, this drops to around about 8 or 9 Hz. And actually, the 2 peaks that we see in alpha range reflect this, that low frequency alpha increases with age and high frequency alpha decreases. And we can visualize this with an animation. So this figure is going to show you a model projection of what our GLM thinks will happen as a participant ages. So we start off at an 18-year-old, and on the right we have the spectrum predicted by the model with a clear peak around about 10 Hz peaking in occipital sensors. And as I play the animation, it's going to show you this participant, this fictional participant aging to age 88 and back again. And what you should see is this peak decrease and move to the left, and the spatial map become more broad, and the alpha peak should end in this lower frequency range. So I'll play that through now. So you can see as the participant ages, this peak decreases and shifts to the left. Now our peak is in this low frequency range. As we go back to being a young adult, in the model prediction, we see the increase in alpha power and the increase in alpha frequency. So our spectrum is able to put a statistical result on top of this. So this is just the effect of age, where we've, I think, shown very clearly some effects that are relatively well established in the literature already. I think what the GLM-Spectrum is able to do is show those effects without averaging over frequency bands and without averaging over channels. And using the power of the model, we're also able to visualize very clearly what type of changes we see across age. One other thing that's really powerful is to have a look at covariate and confound structure that we've also modeled. So remember our first level regressors. So on the left here, we have our linear trend over time. Here are ECG, here are eye movements, and here are bad segments. At the group level, we have really huge statistical effects of how each of these is affecting the power spectrum. In the case of the linear trend, there's such a complicated pattern of effects, I've had to increase the size of the plot. But we can see that each of these has a distinct and substantial effect at the group level. But intriguingly, though this is significant at the group level, it's not exactly the case that they are consistent at the first level. So on these bottom plots, each gray line is an individual participant, and each black line is the group average across all sensors. And what we see is, though these group averages are significant, each individual has a really huge array of effects. So some participants have really 5 times or 10 times more of an effect of bad segments than others. And the same is true for each of our other regressors. And this is where the adaptive nature of the GLM spectrum is important, that where a bad segment is very predictive of the power spectrum, it's able to account for that. But where it doesn't need to do anything, it simply doesn't. At the group level, we can look at the effect sizes of different predictors. So remember, we had 9 regressors, of which 8 were covariates and 1 the mean. We can compute an effect size spectrum to complement our t-stat to look at where the largest between subject differences occur. What we see is that the effect size is largest for the age covariate and for the brain volume covariate. A few of the others, like the hippocampus, show some effect sizes, but these two are certainly the largest. And age, I think we would expect based on what we've seen before, but brain volume is perhaps a little bit more surprising. This is very good quality data. It's been collected very well, and we've done a very thorough pre-processing of it. But the size of the person's head, essentially, is still predicting a large amount of variability in the signal at particular frequencies. Here we can see that the difference between using a model to predict only age compared to a model which includes the full range of covariates. And we can see at the top the effect size. So when we're predicting when we're only using age as a predictor, we get some very substantial age effects. And these are reduced substantially when we add in all of these other regressors. This is expected to be to an extent. If we add any 7 regressors into a model, they're going to absorb some amount of variability. What's reassuring is the t-statistic pattern remains largely the same. The max-min range of t-statistics decreases when we include our covariates, but the pattern of effects remains largely the same. So this age effect is reduced when we add in covariates, including things like hippocampal volume, gray matter volume, head position, sex, and gray matter volume, I think I said already. Okay. When we add all of these extra things into the model, we reduce our effect of age, but it doesn't change shape, and it remains having very large t-values. So this age effect is not completely confounded by these additional things. So again, we've shown that this is able to be reproduced across many datasets, and that it is robust to including quite a wide range of between subject predictors, though it's not totally unchanged by including those. So one other interesting one to look at is the effect of hippocampal volume, because there is a fairly strong correlation between age and hippocampal volume, but by including them both in the model, we can look at the differential effects that each of those has. So again here, I'm going to play a similar animation to what we've seen before, but now we're going to look at what the model predicts is the power spectrum of a participant with a different hippocampus size. So we're starting with the participant with the smallest hippocampus. So this would be most like an older adult. And the animation will play through what changes as we move through to the participant with the largest hippocampal volume. And what we can see is that this has actually a really differential effect compared to what we see with age. So I'll play that through now. Pay particular attention to the low frequency end of this alpha peak. So as we move through our hippocampal volume percentiles, we can see that the low frequency alpha is decreasing noticeably. So participants with a smaller hippocampus have more low frequency alpha, but the high frequency end of alpha is largely unchanged. And this is somewhat similar to the age effect, but actually really separable, that both affect low frequency alpha, but in different ways. And by including them both in the same model and partialing the effects out from each other, we can separate those two out. So the second between subject effect I'm going to talk about is to come back to this point on head size, because I think it is a little bit surprising. This is very well pre-processed data and very clean, but the effect size of head size was nearly the same as the effect size of age. And so here we can see the coefficient spectra of that head size effect for two different channel types. And what we see is that the effect sizes are nearly all, the parameter estimates are nearly all positive, indicating that people with larger heads have more power in most frequency bands. But it's not uniform across space or across frequency. The largest effects follow largely the signal to noise in the data. So these alpha ranges in posterior sensors, where we get the largest alpha signal, have the largest effect of head size. And I think it's very likely that this simply reflects distance to the sensors. People with nice wide heads like me can just about squeeze into the megdua, and our brains are very close to the sensors. But someone who's a little bit smaller, or perhaps a child, would easily get into the meg sensors, into the dua, but that means that their head is going to be that few centimeters further away from the sensors. And this scaling suggests that difference is not uniform across space and frequency. What that means is we can't just apply a simple correction. So if we do something like a Z transform of the sensor data, which has been suggested to help with these kind of things, we see that the effect remains. Now, in fact, we have a more complicated effect where there is a positive effect where we had our largest ranges before, and a negative effect where we had our smallest. So this is our final animation where we're going to look at the effect of head size. So again, watch this alpha peak. So here we're going to use the model to scan through the CAMCAN dataset from the predicted spectrum of the participant with the smallest head size through to the spectrum of the participant with the largest head size. So I'll play that through now. And what you can see is a massive increase in alpha power, essentially, and a slight decrease in low frequency and high frequency power. So what this is suggesting is that distance to sensors indicated by the head size is having a really substantial effect on our power spectrum. What's important to note about this is because we've included this in the model, any between subject effects that this might have or this might interact with have been partialed out of the other regressors. So to a linear approximation, we can be confident that our age effects are not confounded by this head size, though it is so substantial. If we do statistics on this and look at the t-value spectra, we can see when we don't do the Z transform, we get a confirmation that we get one cluster of all sensors, and that covers all frequencies. And the Z transform reduces but doesn't remove this effect. So the main point for this is that our group effects of age and our interesting biological effects, like things like hippocampal volume, are robust to the inclusion of things like head size in our model. However, that's which is good news. It means they're robust. It means they're observable at the group level. However, these confounds are still going to be really critical if we want to look at single subjects. So our group effect is robust. But the implication is that for future work, if we want to look at a single participant within our data set and say, make some inference about their specific medical or health state, we don't just need to know their age and hippocampal volume, we also need to know about these confounders. And those confounders could be additional interesting biological things that might have a real effect. They can be related to the acquisition of the data, so simple things like where the head was in the scanner and what task was being acquired. Or in some data sets, they can be completely spurious. So in this instance, there is a subtle correlation in this data set between age and head size. So this was one data set where around 80 participants were collected, and by chance there is a correlation between age and head size. And if we don't account for that in our model, the head size effect will leak into our age effect. So this variability that we get between these different features, they don't completely confound each other at the group level, but for n equals 1 prediction, we really want to know a participant's head size, because this might be the difference between this being at the top end or bottom end of one of these ranges. So for future work then, we're going to build on these GLM-Spectrum results in two ways. One is by looking at the rapid dynamics of functional brain networks that underpin these frequency changes. So I've described everything using what we call a static power spectrum. So it's a really robust, really well-established way of looking at data, but again is relatively simplistic. We're looking at a very simple view over time. And we can use methods developed by Mark Woolrich's group in Oxford, such as the hidden Markov model or the Dynamo algorithm, to estimate functional brain networks and how they change over time, and see how that relates to the kind of effects that we've been discussing today. And finally, this is all building up to clinical applications. So we've talked a lot today about the effect of healthy aging across the lifespan, but a big purpose to do that is to help detect, identify, and help out with the treatment of participants who have neurodegenerative disorders later in life. So we can see group level effects comparing Alzheimer's disease participants compared to controls. But can we make use of these covariate and confound structures to turn that into really first-rate n equals 1 predictions about those individual participants? So all of our methods are kind of honed in and building up to this kind of application. So I'll close by saying that a lot of the methods on this I've covered today are described in this paper, which is a preprint. It's under review at the moment. We're very close to submitting our revisions. So hopefully you'll see a publication for that in the coming months. We also have a range of tutorials and workshops available online. So if you go to this Open Science Framework page, you can see a set of materials from the OSL workshop earlier in the year. And that contains an entire section on general linear modeling in the context of power spectra. And you can work through a few guided examples of how this kind of method works. Finally, all of the code is underpinned by several important toolboxes. The OSL package, which heavily depends on MNE Python, was used for a lot of the pre-processing and MEG-specific analyses. The power spectrum was computed by the Sales toolbox, and the GLMs computed by the GLM tools toolbox. These are all free and openly available online. So that leaves me to say thank you very much for the invitation again to speak to you today. I hope it's been interesting. Many thanks to my collaborators listed at the bottom, and many thanks to you for your time.
Hi there, thanks very much, Dr. Quinn, that's brilliant. We now have some time for some questions, so please feel free to use the Q&A button if you'd like to. We'll start with this question here. Does it matter if predictors are correlated in your GLM? For example, things like age and grey matter volume are likely to have similar variability across participants.
Yeah, this is an important question because I present it as a strength that we're able to tease apart differential effects when predictors are correlated. And it is really, but this goes against some of the advice people get during regression modeling, which is that multicollinearity or correlation between regressors is actually a bad thing for your model fit. And this can be true. If you have two variables that are very, very closely associated, this can really negatively impact your parameter estimates. In the case we have today, none of that covariability was so large it affected the model fit. And a good thing that you can do to reduce the impact of that is to fit your parameters using what's called a Moore-Penrose pseudo-inverse, which is robust to this type of multicollinearity. If you use ordinary least squares estimates, then they're more likely to be an issue.
Fantastic. Our next question says, on the workflow, you showed bad segment removal. Could you please elaborate on how you do it and what you refer by different there or diff there?
Yeah. So bad segments were computed by in two different. Well, we did something similar for time segments and channels. It's easier to describe in channels, so I'll do that first. So this is simply looking for outliers in the variance across channels. So for each channel, we compute the variance, and then we look at the histogram of that and use an algorithm called the GESD, which basically identifies outliers on that distribution, and we mark those as bad. In the case of time segments, we do this by first dummy epoching the data into, I think, 2-second windows. And then we look at variance within each window across all channels. And we look at the histogram of those and use the same routine, the GESD, to identify outliers and mark those as bad. The diff refers to repeating that same process, not on the raw time course, but on the differential of the raw time course. So the nature of electrophysiology is that there's more variance at low frequencies. So if we do an automated bad segment detection, that's likely to be very skewed towards low frequency information. So taking the differential of the signal is a very kind of easy and cheap way to reweight the time series such that we're more sensitive to outliers in high frequencies as well. Yeah, great question.
So our next one, do the effects of head size still exist in source reconstructed data? This should account for variability in the distance between the sensors and the head.
Yeah, this is another important point that I think also because this is pre-processed data which has had some amount of head movement compensation and head position correction. And all of these things, in theory, should combine to at least minimize individual differences in where the head is and how big the head is. I think the important point here is that all of these methods are necessarily limited by what has been recorded above the noise floor of the system and of the participant in the scanner. So, for example, if in a noiseless environment, if I move further and further away from the sensors, then the algorithm, the source reconstruction weights can simply compensate for that and rescale everything back to what they were before. However, if I move so far away that parts of the signal start to be missed by the sensors altogether, so for example, if part of the signal becomes too small that it falls below the noise floor of the system, then no algorithm, no matter how good, can rescale that back. All they can do is reweight what has been recorded in the data. They can't recover something that was too mixed up in the noise. And that's my best kind of working guess of what's happening with these head size effects. So they are still present in source reconstructed data, and they are quite substantial in source reconstructed data, I think, for this reason. And we were also quite surprised to see that.
Okay, so it looks like we have one final question. How have you computed effect size for a multiple regression model?
Yeah, another good question. So this is using a method called Cohen's F-squared, which will refit the multiple regression a number of times, removing one single predictor from the regression each time. So the effect size and then comparing the R-squared of the full model to the R-squared of the model without that regressor. So what we're seeing is the marginal effect of including or removing a single regressor on the total amount of variability explained by the model. So where we get large numbers, what that means is including that regressor, even amongst all the other 8 or 9 or 10 regressors, is leading to a large change in R-squared. Where we have a small effect size, that means that if we include that regressor or not, we're not really explaining more variability in the data.
Fantastic. I think those are all the questions that we have for today. Let me just double check. Yes, so that's the end of our Q&A section. Thank you, Dr. Quinn, for your time today and for your excellent masterclass session. And to all of our attendees, thank you for joining us, and we hope to see you again in the future. Thank you.